Claude Code and Codex can now read a codebase, edit multiple files, run commands, execute tests, and return a working change for review. You can type a request to add an unread message counter, and minutes later, the feature may appear complete. So what exactly is left for a programmer? Does this mean programming jobs are dying? Let's test that. Imagine you are building a messaging app, and you ask an AI agent to show the number of unread messages beside every conversation. It generates a simple function that loads the messages, filters the ones that have not been read, counts them, and returns the result. The code is clean, the tests pass, and the screen shows the correct number. Would you approve it? Most people probably would. 3 months later, the application begins slowing down. A new user has 20 messages, so the feature feels instant, but an older customer may have hundreds of thousands. Every time that customer opens the app, the program scans the entire message history again just to calculate one number. Now multiply that by thousands of users. Requests begin timing out, the database struggles, and a feature that passed every test is now hurting the entire product. But notice what happened. The AI did not make a syntax error. It wrote exactly what we appeared to ask for, and the failure was hidden inside a perfectly reasonable-looking solution. So you ask the AI to optimize it. This time, it stores the unread count separately. When a message arrives, it increases the count, and when a message is read, it decreases it. Now reading the count is almost instant. Problem solved? Not quite. 2 messages arrive at the same time. Both operations read the current count as 41, and both update it to 42. But what is the correct answer? 43. Or perhaps the database update succeeds, but the network request fails. The operation is retried, and the count is increased twice. Now the code is fast, but sometimes it is wrong. The first problem was about data structures and algorithms, while the second is about concurrency. Ask the AI again, and it may suggest atomic updates, transactions, queues, idempotency keys, caching, or a reconciliation job. Every one of those ideas can be valid, but which one should you choose? Can the count be slightly delayed, or must it always be exact? What happens when an event is delivered twice, or when a service crashes halfway through an update? How much traffic do you expect, and how much complexity can your team maintain? AI can generate possible answers, but someone still has to decide what correct means for this particular product. And that is the part many people miss. Programming was never only about writing syntax. Writing code is a real skill, but memorizing keywords was never the deepest part of the job. The deeper skill is taking an unclear requirement, turning it into a precise problem, choosing a model, understanding the trade-offs, and recognizing where a solution will break. AI is not the first technology to move programmers away from raw machine instructions. Early programmers worked much closer to machine code. Assembly language gave those instructions readable names, and high-level languages went further. When Fortran arrived in the 1950s, programmers could describe mathematical work in a more human form, while a compiler translated it for the machine. IBM gives an example in which work that might require up to 1,000 machine instructions could be expressed using just 47 Fortran statements. That removed an enormous amount of manual coding, but programming did not disappear. The difficult work moved upward. Operating systems hid hardware details. Libraries packaged common solutions. Frameworks automated repeated application structure. And cloud platforms hid much of the server management. Each layer removed work programmers once performed manually, and each layer allowed them to build larger systems. AI is another step in that direction, because it can move us from writing every statement ourselves to describing an outcome, reviewing the implementation, and steering the next attempt. But abstraction does not remove the need for understanding. It increases the amount of power behind each decision. So what should a programmer understand when AI writes the code? Start with data structures, and think of them as Lego pieces that form the basic shapes of a program. A list, set, queue, tree, and graph can all hold data, but they do not make the same operations cheap. AI may choose a list because it produces straightforward code, while a programmer should notice when every lookup requires scanning the entire collection. Data structures teach you to see the cost hidden inside the shape of a solution. Algorithms teach you how that cost grows. A test may show that the program works with 100 items, while algorithmic thinking asks what happens with 1 million. Big O is not important merely because interviewers ask about it. It matters because production eventually asks the same question using real users. Then comes code design. AI can generate 10 files in seconds, but that does not mean those files form a maintainable system. Good design gives responsibilities clear boundaries, limits dependencies, and makes future changes safer. Design patterns help by giving names to recurring design problems, but they are not recipes to apply everywhere. The real skill is knowing when a pattern simplifies the code and when it only adds more machinery. Then the problem grows beyond one program, and now you are thinking about system design. Where should the data live? Should it be cached? And what happens when the database fails? Can requests be retried safely? And do two services need perfect consistency, or is a small delay acceptable? AI can draw an impressive architecture full of databases, queues, caches, and microservices, but a diagram is not a decision. Someone must understand why each component exists and which new failure it introduces. This is why concurrency and parallel programming remain valuable. Code that works when tasks run one after another may fail when they overlap. Two threads can modify the same value, and two services can process the same event. A lock can prevent a race condition but create a bottleneck, while more workers can make a program faster or simply make the wrong result arrive sooner. Not every developer needs to become an expert in GPU kernels or low-level synchronization, but modern developers should understand race conditions, atomicity, ordering, retries, queues, and item potency. People working in infrastructure, databases, games, scientific computing, performance engineering, or AI systems need to go deeper. But perhaps you do not want to think about implementation at all. Perhaps you will focus only on the product and let AI make the technical decisions. That still does not solve the problem. A request to build a recommendation system hides dozens of choices. Are we optimizing for clicks, purchases, or long-term user satisfaction? Should recent behavior matter more than old behavior? And how do we prevent the system from repeatedly showing the same type of content? A language model can quietly fill those gaps with plausible assumptions, and it may build an elegant solution to the wrong problem. Product judgment and technical judgment are not substitutes for each other, because they constrain each other. So how should someone learn programming now? Do not spend all your time memorizing syntax that an editor or AI can produce. Learn enough syntax to read code comfortably, then run it, change it, and debug it. Use AI without outsourcing your understanding. Before prompting it, define the expected behavior, constraints, edge cases, and scale. Predict what kind of solution might work. After the agent generates the code, explain the important decisions back to yourself. Ask about its time and memory cost. Ask what happens when two requests arrive together. And ask what happens when a dependency becomes slow, an event is delivered twice, or a process crashes halfway through. Write the tests the AI missed, and measure the solution instead of trusting how clean it looks. Ask for alternative designs, then reject at least one of them with a clear reason. That is how AI becomes a learning tool instead of a machine that hides your gaps. The role of a programmer is changing, so you may write fewer routine lines by hand and spend more time defining work, reviewing changes, testing assumptions, and coordinating agents. But supervision without programming knowledge is simply approval by confidence. AI can produce code that compiles, but that does not mean it is correct. Correct code is not automatically scalable. Scalable code is not automatically maintainable. And a technically elegant system is not automatically useful. So learn programming, not because humans must remain faster typists than machines, but because someone must understand the assumptions, costs, failure modes, and trade-offs behind what the machine produces. When code becomes cheaper, judgment becomes more valuable. The important question is no longer only whether AI can write a program. Can you tell whether that program is right? And that is why programming still matters.